Excuse me. So what I'm saying is, if I erase this f and put a g here, then it's exactly equation 8. And down 8 is under table 7.2. That's yes. Oh, yeah, fair enough. Yeah, that is something else, which I'll get to next class. Sorry about that. So that's the equation 8 that's floating below table 7.2. If I take this big G and I erase big G and write big F instead, right, and put a little f here correspondingly, then that is now, excuse me, exactly equation 6 in the translation by t thing. So, yeah, that's okay. All right, so here we go. Let's take the Laplace transform of this. So first of all, I need to convert to unit step functions. I'm just going to get straight to it, confusingly write down the thing. So this is going to be, I don't know, 3, I'm sorry, sine of t, fine. Look at you, my mind has atrophied to the point I have to use the gate functions. This is not good. 0 to pi over 2 t plus 3 times the gate function from pi over 2 to infinity t. So that is what? That is sine of t times u of t minus u of t minus pi over 2 plus 3 times u of t minus pi over 2. Okay, I got that out of my system. Finally, my formula for f, which is nice, f of t is sine of t times u of t, all right, and then plus parentheses 3 minus sine of t times u of t minus pi over 2. Now I can take the Laplace transform of this using the formulas we derived. So so here we go. Laplace transform of f of t is, for this one, e to the minus 0 times s, kind of silly, times the Laplace transform of sine t. So this goes to a point. When you've got u of t, essentially, if you've got a u of t in the formula that you're looking at, for our purposes, you can just set that to 1. Because we work with time from 0 to infinity. That's the setup here. So what does u of t say? It says, I'm 1 whenever t is positive, or 0. Whenever t is non-negative, I'm 1. So that's always 1. So you can just drop it. And that's reflected in the formula, because this is 1, which is that. All right, so stupid things aside. Now the next one's more interesting. This is e to the minus pi over 2 s times the Laplace transform of 3 minus the 3, there was nothing to do. But the sign, I replaced t with t plus pi over 2. Right, that's function composition, right? T plus pi over 2. And you're like, well, what do you do with that? Well, yeah, I know exactly. Like, what do we do with that? This, of course, is 1 over s squared plus 1. Get that out of the way. And then we've got plus e to the minus pi over 2 s. And the Laplace transform of, I'll leave the 3. I mean, we could take care of that, but I'll just leave it there. And what's this? Well, this is minus the sine of t, the cosine of pi over 2, right? Minus the cosine of t, the sine of pi over 2, distributing the minus. And what did I just do there? Adding angles formula for sine, right? Now I was nice, I chose pi over 2 because I knew nice things would happen. That makes what? We know cosine of pi over 2 is 0. If you leave cosine of pi over 2 in an answer and you don't put it to 0, I will take off points. I didn't used to, but I've gotten ornery in my slightly older age, and so it just bothers me. Sine of pi. Don't leave sine of pi in an answer. Sine of pi is 0. We know this. This is, something we know. All right. Anyway, and then, so what is sine of pi over 2? Well, sine of pi over 2 is 1, right? So what we have here is a 3. What's the Laplace transform of 3? It's 3 over s. Going back to example 1 last time. Laplace transform of cosine t, well, that's minus s over s squared plus 1. There you go. That is the Laplace transform of this case-wise defined function. This is the hidden wisdom I was operating with when I did the first big picture example last time. Let's do a backwards example to end class here. If I have, f of s equals to, let's say, e to the minus 2s times, I don't know, 1 over s squared plus, s minus 2 over s minus 2 squared plus 49, I can say, what's the inverse Laplace transform? I will use equation star star, all right? So this I identify as the f, all right? So what's the inverse Laplace transform of that f? What's the inverse Laplace transform of 1 over s squared? Is it t? See, this probably be worth adding to your sheet because it's kind of hidden in item 1, 2, 3, 4, 5, 6. If we put a equals to 0 there, and if you put n equals to 1, you get 1 factorial over s squared. So yeah, that's t. The inverse Laplace transform of 1 over s squared is t. And then this is what? That's an e to the 2t, right? Cosine of 7t. So this is my quote-unquote f of t, right? My little f of t, according to the rebranding of the equation after I answered his question. All right. So then the inverse Laplace transform. Oh, I am so sorry. I can't call this f and that f. I need to make a choice, right? So if I'm going to call this f, let's call this thing something else. What do you want to call it? G. All right. Great. So the inverse Laplace transform of g of s is equal to f of t minus 2 times u of t minus 2 using star star, which is actually equal to t minus 2 plus e to the 2 times parentheses t minus 2 times the cosine of 7 parentheses t minus 2. You might notice I'm emphasizing the word parentheses because that's something that needs to be happening here. Anyway, so there you go. That is the inverse Laplace transform of that function. So basically, when you see exponentials in the frequency domain, that is a signature of discontinuities in the time domain. That's how it gets. That's how these piecewise jumps get folded into the Laplace transform. They appear as these exponentials in the S domain, which when you go back, they produce the unit step functions and the jumps in your solutions. I think it's amazing that this works, personally. Anyway, see you guys next time. So sorry I did not finish Laplace transforms today. I had high hopes, but looks like we're still another half hour to go.